These are notes 3.8. So here we want to solve this by factoring. If you remember, with four terms, we're going to use factor by grouping. So we can take an x squared out of the first term and have x plus 3, and take a negative 4 out of that term and have x plus 3. So it gives us the factors of, if you remember, both of those have to be the same. And then what's being distributed through? X squared is being distributed through, and a negative 4 is being distributed through. Okay. We can factor this farther. We have a difference of squares, which would be x plus 2, x minus 2. And then to actually solve it, we want to set them all equal to 0. So we get x equals negative 2, x equals positive 2, and x equals negative 3. Okay. Now by looking at this graph, okay, some things that we know that we know x is negative 2, x is 2, and x is negative 3. We know end behavior, x to the third, will be like this. And we also know the y-intercept is negative 12, so down here at negative 12. So our graph's going to look something like, we don't know exactly what it's going to look like, but maybe something like this. Don't know exactly what happens at the peaks there. Okay, so now we're going to use this equation, which we have right there, and where is it greater than 0? Okay, so greater than 0, where are our outputs? Like, what x's can I put in here to have an output greater than 0? So here, these have 1, 2, 3, 4, 5, okay? So we know from 2 to infinity, okay, so it's not or equal to, so we use that. And also right here, between those two, are greater than 0. So between negative 3 and negative 2. Okay, so the next one says, where is it less than or equal to 0? So right here, these points right here would have y's that are less than. So that's from negative infinity to negative 3. And it's or equal to, so we're going to include the 3, negative 3. Also right here, all these y's, all these outputs are less than 0. So between negative 2 and 2. Okay, next problem. Solve this by factoring. Okay, when there's three terms, we set up our two parentheses. Be x squared times x squared, and negative 10 and a positive 4. Gives me what I need there. Now neither of those can be factored, so we'll just solve them now. So I add the 10 over, take the square root, so we get plus or minus the square root of 10. And this one, we get negative 4, take the square root, we got plus or minus the square root of negative 4, which is plus or minus 2i. Okay, so by looking at this graph, the square root of 10 is about 3.16. So 3.16, they're negative, and 3.16 positive. Okay, so it's going through there. I know the y-intercept is down here at 40, negative 40, way down there. And I know it's a x to the fourth positive, so I know my end behavior is up. So it's going to come down through here. Now it's going to do some kind of weird thing because we have two imaginary answers, so I'm not sure what exactly it looks like, but maybe something like this. Okay. So where is this equation greater than or equal to 0? So right here and right here, those are answers that are have positive y's, right? So from negative infinity to negative square root of 10, okay, it's or equal to. Where is it less than 0? So this whole area here is less than 0. So, and it's not or equal to, so parentheses. So from negative square root of 10 to positive square root of 10. Next problem, we want to solve this by factoring. So three terms, we're going to set up our parentheses. to try 4x squared times x squared. If that doesn't work, you could try 2x squared and 2x squared. I think this will work though. If we get this, that'd be 4 minus 9 is negative 5. And this is a difference of squares, so 2x minus 3, 2x plus 3. These are squares, but that's not a difference, so that cannot be factored. Set them equal to 0. Add your 3 over and divide by 2. Subtract your 3 over, divide by 2. And this would be x squared is equal to negative 1. Take the square root, you got 1i plus or minus. Okay, so we have our solutions. Okay, this one, to solve it, we first want to get it equal to 0. So put it in the right form from descending order. So minus 3x squared, and then we'd have minus 8x and plus 12 in standard form. Okay, 4 terms. We're going to use grouping. So I can take out an x squared there and a negative 4 here. Okay, so my factors are 2x minus 3, and the x squared is being distributed to that, and the negative 4 is being distributed to that. Okay, to solve it now, if I set these both equal to 0, add the 4 over, take the square root, I get plus or minus 2. And if I add the 3 over and divide by 2, I get that answer. This one here, solve by factoring again. Let's get it in standard form. So minus your 6 with 3 terms. Set up your 2 parentheses and figure it out. X squared and x squared give you x to the 4th. Plus 3 and negative 2 gives me 3x squared. Minus 2x squared is 1x squared. Okay, we got to set them all equal to 0 and solve. So I'm going to add that 2 over and take the square root. I'm going to subtract the 3 over and take the square root. So it's a negative, so it's I. Okay, number 10. We want to show that 2 is a solution to this, and then find all the others. So there's 3 answers, so I'm going to find 2 other answers to it. So to show that 2 is a solution, let's divide it out and see if it works out evenly. If it doesn't, then it's not. So 1 and 3, negative 11, 2. Synthetic division. Be 2, additive is 5, 10, add is negative 1, multiply. Okay, so since this is 0, we know that 2 is a solution. Okay. Now, to find the other ones, okay, we got to take this now. This is going to be x squared plus 5x minus 1, and we have to solve this now. Well, I'll write them as factors. Okay, so I know if this answer is 2, our factors would be x minus 2, and then this one right here. Those are our factors. And now we need to solve them. So I know that x equals 2 for this one. With this one, I'd probably use the quadratic formula. Okay, and you get negative 5 plus or minus the square root of 29 over 2. Okay, this one here says to use the graph, so you can go to Desmos and graph this. I'll just tell you that it looks like this. And our points here are negative 1.37. Right here it's 0.33, and here is 2.32. Okay, so where is it equal to 0? Well, at those 3 points. Okay, so that's where x is equal to 0. Where is it greater than 0? Okay, greater than 0 would be here and here. So from, it doesn't say we're equal to, so negative 1.37.33. Then also from 2.32 to infinity, from here out. Where is it? Less than 0. So less than 0 would be this area right here, and also this area right here. So from negative infinity to here. And also from 0.33 to 2.32. Okay, complex nth root theorem. Basically, kind of get into this. Yeah, let's work this out. Find all sixth roots of 64. That basically just means we want to solve this equation right here. Okay. The actual theorem says if I have x to the n is equal to k, this has exactly n complex roots. Okay, but if we want to solve this equation here, I'm going to try and use some factoring techniques. So I'm going to get it equal to 0 first. Okay, this is a difference of squares. X to the third times x to the third minus 8 and plus 8. Okay, remember our factoring here, we got some cubic patterns. So x times x times x, 2 times 2 times 2. So you have x minus 2. X squared, that's minus, this is plus 2x, and then 2 times 2 is 4. This one over here is going to be x plus 2, and just switch the sign there. Okay, so to solve this, we're going to find 6 different answers here. This one's pretty easy, that's x equals 2, got 1. We got x equals negative 2 here, that's 2. Okay, and to solve this, I'm going to have to use a quadratic formula or completing the square. I'm going to choose completing the square. So add 1, remember half and square it. X plus 1 squared is equal to negative 3. X plus 1 is equal to plus or minus the square root of 3, which gives us x equals negative 1 plus or minus I root 3. So that's 2 more answers. I have to do the same thing over here. So add 1. This is x minus 1 squared. So you can see the same pattern here, just the sign here at the end. So x minus 1 is equal to plus or minus the square root of 3. X is equal to 1 plus or minus I root 3. Okay, so it gives us all 6 answers there. Okay, the fourth root of 81, all fourth roots. So we're basically finding x to the fourth is equal to 81. If I factor it, difference of squares. This is another difference of squares. And this isn't a difference that doesn't factor. Okay, now to solve it, I'm going to set them all equal to 0 and solve, so I get x equals negative 3. X equals 3. Okay, this will give me x squared equals negative 9. Square root of both sides, I get x equals plus or minus 3i. So 3, negative 3, 3i, and negative 3i would be the 4 roots of 81. Okay, some word problems now. A box with an open top will be constructed from a 12 by 20 foot piece of cardboard. So I know from here to here is 20, and from here to here is 12. Write a function for the volume. Okay, so remember how we did this? We cut out a certain corner here, and that's basically the height, if you think about these 4 sides being flipped up. And then our actual box size would be what's left there. Here, this would be 20 minus 1x, 2x's. And this distance here would be the whole distance, which is 12 minus x minus x is minus 2x. So it'd be 20 minus 2x times 12 minus 2x times 8, which is just going to be our x. If you multiply that all out, you use all your distributing and stuff, you will get 4x to the third minus 64x squared plus 240x. Okay, locate a point on the graph so you can use Desmos and get that graph. Okay, so this gives us that volume. So we can take that and we can graph it on Desmos. And if you just pick any point at all, I'll just pick this point, 3.6 and 221.2. Okay, think about what that means. So it means that if my x is a 3.6 and x was this corner, right? If we cut out a corner, 3.6 inches, okay, then the volume will equal of the box 221.2 inches cubed. So we have our corner cut in inches here as the x, and our volume in inches cubed as our y. Okay, what size will the box be when the volume is maximized? Okay, if you remember, the maximum occurs at the vertex. So you can use negative b over 2a, or look at it on Desmos, and you get the point 2.43 and 262.68. Okay, so what is the size of the box? Okay, so we know this is our max volume, but the size of the box, okay, so if you think about this, you know the height is going to be this, right? But if I take 20 minus 2 times that, that gives me 15.14. And if I take 12 minus 2 times this, that gives me 7.14. And I know that the height of the box is that x. So those would be the dimensions of the box to give us this volume. Okay, that would be the most volume that this box could have if we start with 12 by 20 with cutting out corners. For what x is the volume equal to 200? Okay, so if you think about the graph here, okay, I don't know, it goes like this, right? So if we think about where 200 is, and think about where that is, there's 2 points where it's equal to 200. So equal to 200 at 1.17, so here's 1.17, and at 3.9. So right here is at 3.9. So if I have x's, the dimensions of these corners are cut out to be this, I will have a volume of 200. Okay, where is it greater than 200? So right here, right between here and here, we have it greater, right? It's over 200. So between 1.17 and 3.9. So any x that's between those two will have a volume greater than 200. And less than 200 will be this part over here. So if I use a different color, it would be this part here and this part here. So you really can't go negative with an x, right? You can't have a negative distance. So we're going to stay from 0 to 1.17 and from 3.9 and all the way down here to 6. Okay? You could say, yeah, we have to stop there because we can't go negative with our volumes and so forth. Those are restrictions. Wait, last problem here for the chapter. The table shows the number of transactions in billions users of bank debit cards. So in 1998, there were 3.7 billion transactions on people's debit cards. You can see they keep increasing. Okay, so they keep increasing. Find a cubic model with x equals 0. Okay, so this is, we're going to put in 0. This is 2 years later. This is 2 years later after that. This would be 6, and it'd be 9. Okay, so we're going to use a(x1 to the third plus bx1 squared plus cx1 plus d. Okay, so you're typing that in, and you get a model of p of x is approximately, because I'm going to round it, negative 0.0138x to the third plus 0.2253x squared plus 0.7776x plus 3.7524. Okay, if you round it differently, you get some different numbers, but you get the main idea. Okay, part B. Use the model to find the number of transactions in 2005. Okay, 2005 would be 1 year out of this, so it'd be x equals 7. So if I plug x equals 7 into the equation, I get approximately 22.5 billion transactions. Okay, how did it compare to this? It was 0.2 billion below. But it was close. Okay, so our prediction was pretty close to what actually happened there. Estimate when it will reach 30 billion. Okay, so 30 billion is the transactions with our y, so I want to plug it in for the y. So I want to solve this equation. Okay, so to solve that equation, I think using Desmos is probably the easiest thing. Look at where does y become 30, and it's right around where x equals 10. Okay, it's pretty close to where x equals 10. So if this is 0, 10 years later would be 2008. Okay, so in around 2008 we'd have reached 30 billion.